Black holes are the scariest, strangest, and most horrifying objects in our universe. So what if I threw you into one? And I mean that. Einstein is said to have described these beasts. He didn't even really believe that they existed in our universe. But we found them. So let's do it. Let's send you on a journey plunging into a black hole, and watch how the laws of physics begin to break down, and some of the mind-blowing phenomena occur. Now, as you watch this video, I need you to remember just one thing. This is not science fiction. This is real physics. And at times it might be hard to believe, but I can prove it. Are you ready? When massive, extremely dense stars get to the end of their lives, they collapse and leave behind nothing. There is no surface to walk on, no physical surface to touch. What it creates is known as a singularity, a single mysterious point in space-time that is said to have infinite density, and therefore infinite gravity. Einstein's general theory of relativity really gives us one revolutionary idea. Gravity is not a force acting on objects. It's simply just space-time itself bending as a result of an object's mass. It completely explains how we are in orbit around the sun, and perhaps more interestingly, why black holes are even black. Like I said, when you're looking at this black hole, there is no physical black surface out there in space. The singularity hidden inside is simply so dense that space-time is warped so much that it creates a well with vertical walls. This makes it impossible for anything, even light, to escape. Because to escape, something with this much gravity would require you to go faster than the speed of light, which we both know is impossible. When Einstein looked at this result, he wasn't convinced that nature would allow something this ridiculous to exist. In 1939, he published a paper arguing that this idea of a star collapsing into a singularity was not convincing and didn't really occur in our universe. Ironically, that very same year, Oppenheimer, published a paper alongside fellow physicist Hartland Snyder that predicted stars really could collapse under their own gravity into a black hole. The best part about black holes is that anything can become one. And I mean that literally, even you. Karl Schwarzschild, a German physicist, was the first one to discover an exact solution to Einstein's field equations. It's kind of simple and beautiful in a way. This is really just saying that any object of mass m, whether it's a star, a planet, or a little human, can become a black hole if it gets squished to fit inside this Schwarzschild radius, r. Let's take our sun, for example. If you squished all the mass in the sun down into a sphere with a radius of just 3 kilometers, you would get a black hole. What about the Earth? Well, that would be a sphere with a radius of around 9 millimeters, about the size of a marble. A human, on the other hand, would have to be squished down so unbelievably small, much smaller than even a proton. But if you did become that small, you would be a black hole. Weird, right? I think it's finally time we send you into a black hole, but which one should we pick? We could pick a small one like this, but that seems boring. Let's go bigger. What about these behemoths? These black holes have larger event horizons than our entire solar system. We are talking billions of suns worth of mass, but that's too much. Why don't we go for one a little closer to home? Sagittarius A, the supermassive black hole in the heart of our very own Milky Way galaxy. You are orbiting it right now, and it's one of only 2 black holes that we have taken a picture of. Let's assume that you and I fly out there and park the spaceship 1 trillion meters away from the event horizon. We are going to send you out towards the black hole, and while you free fall in, I will stay on board the spaceship and watch. But here is the key fact. General relativity tells us the way time is experienced by a person near a black hole can be drastically different because space-time is so intensely warped by the black hole. We saw that in Interstellar. So to keep track of time, we give you a special watch that will tell you how long has passed from your perspective and from my perspective back on the ship. We sync the watch and away you go on your journey for the black hole. As your journey begins, you see the distant monster rapidly consuming material, causing it to be superheated due to friction. This simulation would have taken more than a decade to run on your typical laptop. The disk in real life would be a bright blue or even white color, but in this case it's been made orange for visibility reasons. You check your watch for the first time. Only 30 minutes has passed, and you're about 0.1% of your way to the event horizon. So far, I've only gained 11 seconds back on the ship. Not too bad. Now we are getting closer. The curved space-time around the black hole is causing all kinds of strange visual effects. Light rays from the sides and even behind the black hole are being bent around it before arriving at your eye. Let's check the time again. You've now been gone for 2 hours, and you're 1.4% of the way there. I'm now 44 seconds ahead back on the ship. Slightly alarming, but nothing crazy. The shadow of the black hole, that dark region in the middle, appears to be growing quicker than we should expect. Again, due to that gravitational lensing effect that bends light rays that would normally pass by you into your retina. After a long time, you finally check your watch again, and what you find terrifies you. From your perspective, you left around 12 hours ago. But for me, back on board the ship, I've been watching you float towards the black hole for nearly 15.5 hours. We are getting close now, and things are about to get pretty weird. But before you reach the point of no return, you come across a strange and seemingly magical place. If you were frozen in time at this one special spot and looked around, you wouldn't believe your eyes. You have arrived at the photon sphere, maybe the strangest place in our known universe. This is a region of space around the black hole where gravity is perfectly balanced such that light can actually orbit the black hole. Not matter emitting or reflecting light, just the photons of light themselves stuck in orbit. If this light moves tangentially to the black hole, it can orbit. But any tiny variations in its path will either cause the photons to fall into the black hole, or simply fly off into space. Under these very specific conditions, if you just froze at the photon sphere and looked around, you would see mirror images of yourself looking away from you. You'd see a number of copies of the back of your head staring off into space. You are literally seeing yourself, essentially stood right beside you in real time with no technology or anything. Just the warping of space-time itself. And here's where things get crazy. As you continue your journey, you are getting really close to the event horizon. Now we are past the photon sphere. The black hole seems to be taking up more of your view than you would expect. It kind of feels like you're being swallowed by darkness. This is because the darkness is being warped around you, showing the back and sides of the black hole's shadow in addition to the part that would normally be visible to you in flat space-time. You have now been gone for 13 hours, and in 24 minutes you will cross the event horizon. But from back on the ship, I've been watching your journey for nearly 20 whole hours now. 18 minutes later and you check again, and now I've been watching you for nearly 40 hours. The last 18 minutes for you lasted 18 hours for me. And finally, it's time. After just 6 more minutes, you cross the event horizon of the black hole. You close your eyes, take a deep breath and look at your watch, but it seems to be broken. It's saying I've been watching you fall in for an infinite amount of time, but it's not broken. The physics is right, and I spent decades watching you slowly edge closer and closer and closer to the event horizon. Eventually I see you become redshifted. This means I have to use an infrared telescope to even see you. I never get to see you cross the event horizon, even if I lived forever. The last 6 minutes of the journey for you literally lasts an eternity for me back on board our ship. I know this sounds like science fiction, like a complete fantasy, but it's not. It jumps right out of Einstein's equations. Now you are inside the event horizon. So what happens here? Strangely, you'd actually have a pretty hard time knowing when you cross the event horizon itself. You can still look out into the universe, seeing distant stars, and even seeing our ship floating out there in space. But all of that light, just like you, is entirely destined to head to the singularity now. You are past the point of no return. That point of infinite density, where our laws of physics collapse and time simply stops. To escape the pull of the singularity, you would need to travel faster than the speed of light, which we know is impossible. A common misconception is that if you looked out into the universe, this intense time dilation effect would cause you to watch the entire future history of the universe unfold in front of your eyes. But this is just not true. Due to an effect called aberration, as you get close to the singularity, you'll watch the outside universe get squished into this thin little ring. And finally, once you are close enough to the singularity, your feet would be stretched out in front of you, dislocating your body in a process known as spaghettification. You and the black hole are one, wandering the universe together for eternity.